Okay, good afternoon, everyone. Thanks for coming to my talk. My name is Caitlyn. I'm a second-year PhD student here at Monash University, and I work with Daniel Price and Christoph Pant. And today I'm going to talk to you about whether or not there is turbulence in a protoplanetary disk known as DM Tau. So here's a plot you may or may not have seen before. Basically, it shows the demographic of discovered exoplanets that we have. So along the x-axis, we have separation from the host star, and along the y-axis, we have mass of the planet. It's quite easy to divide this plot into two. As you can see here. On the left, we have planets that have been discovered by more traditional methods, such as the radial velocity and the transit method. Whereas to the right, so the more further out planets, we've been filling up this area of the parameter space with planets detected by interactions with their disks. So these are baby planets which have been forming in these disks. And so this has been good for us because we, of course, want to learn about how planets are forming. And with the progressions in technology, such as that with the ALMA telescope, we've been getting more and more high resolution data to look at these disks and get planets in the early stages of formation. So I'm part of the EXO-ALMA collaboration, which is an ongoing ALMA large program. And we've been looking at 15 different protoplanetary disks and primarily to look for planets in them. So here we have the continuum emission of these disks. So that's basically just the emission from the dust in the disks. I've been primarily focused on one of these disks, which I'll talk to you about in a little bit. But aside from looking for planets in these disks, one other thing that we've been interested in particularly is questions about what drives mass accretion and angular momentum transport in disks, because this is currently an unknown problem. Processes such as these are important for things like planet formation because it controls things like the location and growth of your dust grains, planet migration once the planets have formed. So we kind of want to understand what's going on here. And one thing that might be responsible for these is turbulence. So basically your turbulent motions in the disk. So most disks have been measured to have turbulent velocities of about less than 10% of the sound speed, whereas one disk, which is my favorite, DM Tau, has been proposed to have non-zero turbulent velocity. So here I'm showing you a cube in velocity space of the disk. So basically we have the CO gas emission in the disk moving towards and away from us. So basically each frame in this image is a slice in velocity through the disk. And this is what we look at when we do the modeling of the disks. So there's a paper put out by Flaherty in 2020 where they modeled DM Tau. They used a fixed central stellar mass in the disk, and they fit for a bunch of disk parameters, such as things to do with the temperature structure of the disk, obviously the geometry of the disk, and obviously turbulent velocity in the disk. And they found that the turbulent velocity was about 60 to 80 meters per second, so 25 to 33% of the local sound speed. And here are a couple of plots showing how they justified their fitting, I guess. So here on the right, we can see it represented like in that movie in the image plane. So basically, these are the different channels that we have. The models obviously line up with the data, you subtract them, you get minimal residuals. On the left is the line profile of the disk. So basically what you do is for each channel, which represents the x-axis, you just sum up all the flux in each channel, you get out the line profile. And what they saw was that obviously, if you have more turbulence in your disk, you have a broadening in each of the channels here. So say in systemic velocity here, you get wider channels if your disk is more turbulent, as well as in this peak to trough ratio here. So they needed to have more turbulence in the disk to reproduce these features. When I started my PhD and I was learning how to do disk modeling using Christoph's code MCFOST, which has a now funky new logo. So that's a 3D radiative transfer code, which can model both the dust and gas in the disk. And it uses a Monte Carlo method to sample specific intensity, do ray tracing in the disk. It also couples with hydro codes like Phantom. So we were mucking around with the modeling, and what we found was you could reproduce the broadening in the channels by changing the central stellar mass. So as you can see on the left, if you have a lower stellar mass, you have broader channels. Increasing it decreases the size of the channels. So we were quite interested in that. And when we compared it to the observations of DM Tau, obviously there's not as drastic of a change in the size of the channels here, but we discovered that you could still quite well match the observations with a lower stellar mass with no turbulence in the disk. So then what I did was I ran a grid of models, only varying the turbulent velocity and the mass of the central star. And we found that there's a range of masses which are consistent with having no turbulence in them, which produce a very good fit to the data. And for comparison, that's where that paper would fall on that. So obviously we're very interested in seeing if perhaps the fixing of the central stellar mass resulted in an error in getting the turbulence out. So from ALMA, you don't get just images out, unfortunately. So I'm going to take a quick detour into radio astronomy land and talk to you a bit about visibility space. So ALMA is an interferometer. So basically it's constructed of a bunch of different antennae. And what we measure from ALMA are signals at each antenna. We multiply and integrate these signals, and what we get is a measure of the coherence between these signals. And that's what we call visibilities. So for some pair of antenna at UV points, which are points on the ground, we get a 2D Fourier transform of the sky brightness distribution. So these U and V are Earth-based coordinates, your L and M are sky-based coordinates. It's an ugly equation, I know. It took me a long time to wrap my head around this. But basically what is happening is a Fourier transform from visibility space spits out the image. So that's what you get from ALMA. So that's what we wanted to do our fitting to. And that is what the Flaherty paper originally fit to as well. Yep, so with ALMA, you have your bunch of telescopes there. And the way that they get more UV points out is they move the telescopes around on the ground to trace out these tracks like you can see here. And the aim of the game is to fill up as much of the UV plane as possible in order to do your Fourier transform. Obviously, we can't always fill it all the way up, but we try very hard. And also the rotation of the Earth also traces out some of these tracks. So that's how we get more UV points. So I've been doing lots of disk modeling the past year. So basically the way that it works is we generate synthetic observations using MC-FOST. So basically for each model, I construct a cube in velocity of the disk with a bunch of different parameters, which I will list here. So lots of different geometrical properties, as well as things like turbulent velocity and different like dust and gas mass things. And so you can use that to fit in the image plane, or you could also then go into the visibility plane. So what we do is pass the MC-FOST models into another code. So the one I'm using is CSALT, which has been written by one of our ExoAlma collaborators. So the past little bit, I've been working on making an interface between these two codes, so that way we could use MC-FOST as an input. And basically what CSALT does is it transforms the model into visibility space, so we can generate model visibilities, compare these visibilities with the ALMA visibilities, subtract them and get residuals. And then we want to run an MCMC to find the best fit parameters. So here is a plot showing my best image plane fit. So this was done without going into the visibility range. So as you can see, it's not perfect, but we have been getting out a lower turbulent velocity than what Flaherty proposed, so 23 meters per second compared to 60 to 80, as well as a lower central stellar mass. When we look at our visibility fitting, so I've got the model to model working in visibility space, which is great. It took a lot of effort. I was really happy with that when that finally worked. And so I've listed here some of the parameters, or all the parameters that I used and what the retrieved values were. So as you can see, the important one is the turbulence. So we injected 0 turbulence. We retrieved 4 meters per second turbulence, but within errors, it was consistent with 0. So that was very exciting. Unfortunately, we're still working out some bugs in the code, well, probably on my end, and I'll let you witness my public shame. When we fit the model to data, something is going wrong. Fortunately, in this case, it looks like there's just a minus sign missing somewhere for the PA, so we can just rotate the disk and hopefully it'll settle down a little bit, so not great. But yeah, hopefully that gets resolved soon. That's what I'm currently looking for. Hopefully it's a quick fix. Yep. So our takeaway points is that using this new high resolution data from ALMA, we want to constrain protoplanetary disk parameters better than ever before. We can model these disks using radiative transfer codes like MC-FOST compared to the observations in both image plane and visibilities. So our model to model fitting works now, which is great. And we look like we can retrieve the 0 turbulence if there is some, or at least turbulence that is consistent with 0. And the model to data fitting still needs some extra prayers. So hopefully that works out soon. Thank you very much for your time, and I'll happy to answer any questions.
Very interesting work. Could you give us an intuitive explanation for why lowering the mass allows you to infer a lower turbulent velocity? I don't quite follow how that.
It just
works.
they kind of had the same, like it appears to do the same thing. So if you're looking at it, say in terms of like your image plane fitting. So basically when you have more turbulent velocities, what that means is the gas that would ordinarily be in another velocity channel can get dispersed out into other channels, so it can broaden them. So basically that's why we see them, like the channels are getting broader. When you have more mass, obviously, like then you have like
lower mass gave you lower turbulence. Is that right?
Lower mass and lower turbulence can replace your higher mass and higher turbulence.
Yeah. So that's what I was trying to understand. I could have maybe thought about it the other way. Yeah. Anyway, we can talk about it afterwards. It's very interesting. Thank you.
I repeat, it's very interesting. I was wondering, I forgot what I was wondering because I was thinking about Stan's question. I will let you know if I remember it, and I'll approach you.
Yeah, I think this will be the last question.
Hey, yeah, very interesting talk. I was wondering do you ever consider anything like resident interactions for like remote angular momentum transport through from the side of the?
No.
Should we have time for one more? So any more questions? Did you remember your question?
Before I forget it again, the central star, except of the constraining the mass with the disk, I guess, I mean, you find the mass which is almost half of what was previously mentioned. I guess such stars look very different spectroscopically or photometrically. So
yeah, well, it is quite a young star, so does still have all the disk around it. So yeah, I guess. Well, I guess what we're trying to fit is luminosity, because predominantly all of the flux would come from a central star, right? I think in MC-FOST we have like the mass, and then you also provide a radius for it. But then, yeah, what we're fitting for is the luminosity that's output here.